So this says the function a is given by that, so it's an accumulation function. Determine the coordinates of the point of inflection of the graph of a of x. So the point of if I want to find something about the point of inflection, I want to figure out when a double prime of x is equal to 0. So I'm given the function a of x, which is equal to the integral from 0 to x of t squared minus 2t dt. And so to find a prime of x, what that means is I want to find the derivative with respect to x of the integral from 0 to x of t squared plus 2t dt. So I'm going to apply the fundamental theorem of calculus, part 2. So if you don't know what that states, then you should go look it up and take a look at the statement of that. But basically, when I apply the fundamental theorem of calculus, part 2, I get that a prime of x is equal to x squared plus 2x. And so one way to think about the fundamental theorem part 2 is the idea that this derivative and integral kind of undo one another and you kind of get back to where you started. So that is a prime. So to find a double prime of x, we're just going to take the derivative of that. So I'll get 2x plus 2. If I set that equal to 0, I'll get x is equal to negative 1. And so, so that's the x coordinate of the inflection point. Maybe I should check that that it actually changes concavity. So I'll just put a double prime here. I'll put negative 1 here. I can test points on either side. So a double prime of 0 and maybe like a double prime of negative 2 and just make sure that the sign actually changes. So a double prime of 0 is 2, which is positive. And a double prime of negative 2 is negative 2, which is negative. So that means that a is concave down on this portion of the graph and then concave up. So there actually is a change in concavity at x equal 1. Then to continue to find the coordinates at the point, I also need to find a of x. Sorry, a of 1, negative 1. So I need to actually evaluate this integral from 0 to negative 1 of t squared minus 2t dt. And so I can compute an antiderivative of that. So an antiderivative of that would be 1/3 t cubed minus t squared, evaluated from 0 to negative 1. So by the fundamental theorem of calculus part 1, I can plug in those endpoints. So 1/3 times negative 1 cubed minus negative 1 squared minus 1/3 times 0 cubed minus 0 squared. So that's all going to just be 0. So you end up getting negative 1/3 minus 1. So it's negative 4/3. Okay, for the next one, it says Yvonne decided to go for a run after school. She wants to start from her home. The function v of t expresses Yvonne's velocity t minutes after she started running. What quantity does the following sum approximate? So let's just analyze this a little bit. So this is going to be some sort of a Riemann sum. So I think it might help to just plug in a few values. So if I look at the first value, it's going to be v of, if I plug in k equal 1, it'll be 4 plus 0 over 2. So v of 4 times 1/2. Plus, when I plug in the next value, it's going to be v of, when I plug in 2, it's going to be 2 minus 1 over 2. So that's just going to be 1/2. So 4.5 times 1/2 plus v of, well, it's just going to be 5 times 1/2 and so on. The last one that I plug in, when I plug in 6, it'll be 4 plus 5/2. So v of 4 plus 5/2 would be 6.5 times a half. So what that's saying is that the velocity is this part, and then the amount, a change in time is given by this 1/2, right? So I'm looking at these values from 4 to, well, the last one that's plugged in is at 6.5. So, but this is going to be a left-hand sum, I can tell. I'm taking the left-hand value of each thing to compute the velocity. So it'll be the velocity from, or the amount of distance from 4 to 7 minutes. So this should be the change in Yvonne's distance away from home, because this is a velocity times time. So that's going to give us a distance. So what I'm doing is I'm adding up the distances for each of these half-minute time intervals. So it'll give me the total change in distance from the time interval t = 4 to t = 7. Okay, so the next one I have, suppose that the integral from -2 to 9 is 12. So -2 to 9 of f of x. So f of x is some function like this. And then I know the interval from 2 to 9 . Oh, sorry, 3 to 9. And then I'm asked what is the integral from -2 to 3. So what I know is that the integral from -2 to 3 of f of x dx plus the integral from 3 to 9 of f of x dx should equal the integral from -2 to 9 of f of x dx. So what I'm given is I've given a value for this one. So I know that one is equal to 12. And I'm also given a value for this one. I know that that is equal to 4. So I can solve for this one. So the integral from -2 to 3, it should be 12 minus 4. So that should be 8. Now it says evaluate each of the following. So I just need an antiderivative here. So I know that tangent has derivative secant squared. So an antiderivative of secant squared is going to be tangent of t minus, and then I have a 9, and then I'll have t, and the power of t is going to go up by 1 times a third, and then plus c. So if you want to write this as tangent of t minus 3t cubed plus c. If you want to simplify, you can do that. Okay, for this next one, I need to make sure that I am doing a u substitution. So we're going to let u equal x squared, the inside function, inside that e function, and then du will be 2x dx. And so what I need to do is I'll do the integral from 2 to 3 of e to the x squared. I'm going to write that x right over here by the dx, x dx. And I really want a 2 to show up there, so I could do a 2x dx and a 1/2 out here. And that way my du will be sitting there. So now I'm ready to change everything over to be in terms of u, except I do need to deal with the bounds. So I know these bounds are x values. When I convert them to u values, I want to use this relationship between x and u to convert those to u values. So when x is equal to 2, u is equal to 2 squared, so that's 4. And when x is equal to 3, I know u is equal to 3 squared. So this will be the integral 1/2, integral from 4 to 9 of e to the u du. And then an antiderivative of e to the u is just e to the u, so I'll have 1/2 e to the u, evaluated from 4 to 9. And then that'll be 1/2 times e to the 9th minus 1/2 times e to the 4th. So that's my final answer there. For the next one, I can see that I have a fundamental theorem of calculus part 2, because it's the derivative of an integral, but my bound is a function of x. So this will be, chain rule will be combined here. So my first, using the fundamental theorem part 2, I'm going to replace the theta with that function of x. So it'll be cosine of 2, and then that function of x is x to the 4th plus 1. And so that's the derivative of the outside function. Then I need to multiply by the derivative of the inside function, which is the x to the 4th. The derivative of x to the 4th is 4x cubed. And that's the final answer there. For the next one, it says Courtney's velocity while running a marathon is given by this velocity function. And so the first thing says write a sentence explaining the meaning of that expression. So I'm looking for, this is going to give me this expression gives the net change in distance from t equals 1 hour to t equals 3 hours. So that will tell us in that 2-hour time period, how far did Courtney go, or what is her change in distance. Okay, now it says a marathon is approximately 26.2 miles. Given that the integral below equals 26.2, write a sentence explaining the meaning of x in the context of this situation. So the x is a top bound. So if I look in this one, I notice that the 1 and 3 are time values, right? So I want to know the amount of time. So from 0 to what time value will her total distance equal 26.2? So x represents the amount of time that it takes for Courtney to run 26.2 miles. So her total amount of distance, change in distance from time 0 to time x is equal to 26.2. So if we could figure out what x is, that would tell us how long it takes for her to run that total amount of distance. Okay, so the next one, I'm given that oil leaks out of a tank at a certain rate. And then it says, which of the following represents the exact amount of oil that leaked out of the tank from 15 to 45 minutes? And so what I can see here on part 2 is going to be the exact amount, because it's going to be the rate, the integral of the rate at which the oil is leaking. So this is one of the exact amounts. The other one, the next one, 3, this is a Riemann sum. So this is an approximation. And it does have 60 rectangles, so it might be a decent approximation. But it's not an exact value. This one here, I'm taking the limit as the number of rectangles goes to infinity. So this one will be an exact value. And in fact, this is the formal definition of what an integral is. It's a Riemann sum, and then you let the number of rectangles go off to infinity. So the correct answer is 2 and 4 only. Okay, the next one says, let f of x be greater than 0 and f prime be greater than 0. So if f of x is greater than 0, that means f is increasing. F is positive, And if f prime is greater than 0, that means it's an increasing function. So it might be increasing in concave up, or it might be increasing in concave down. Either way, we have an increasing function. Okay, then it says, which of the following approximations is the largest? So, I'm doing from 2 to 4. And if I look at these Riemann sums, I can break this into 4 pieces. And I can look at these Riemann sums. I can see that a right-hand sum would be the biggest one for this one. And similarly, for this one, our right-hand sum would also be the biggest because it's going to go over the green line, over the graph. So whether it's concave up or down, it doesn't matter. The right-hand Riemann sum will be the largest. The left-hand Riemann sum I could see would end up being below, right? So it's going to be smaller. So that will be the smallest. But the largest will be the right-hand Riemann sum. For the next one, it says evaluate each of the following. So I'm just going to find an antiderivative here. So I'll get 18 times x to the 6th, and then I'll have a 1/6 in front, minus 10 times, I'll have x to the 5th and a 1/5 in front, minus, when I have 1 over x, an antiderivative of that is natural log x. So I'll have 28 natural log absolute value of x plus c. If you want to simplify, I'll have 3x to the 6th minus 2x to the 5th minus 28 natural log absolute value of x plus c. Okay, here I want to find a definite integral of t to the minus 2. So I'm just going to rewrite this as t to the minus 2 dt. So I can just go ahead and find an antiderivative of that. I don't have to do a substitution or anything. So the power is going to go up by 1. So that'll be t to the negative 1. I'll divide by the new power, so that'll just make this negative. I'm evaluating that from 1 to 3. So that'll give me negative 3 to the negative 1 minus negative 1 to the minus 1. So that will give me negative 1/3, and then the minus will make a plus. 1 to the minus 1 is just 1, so this will be positive 2/3. Okay, for the next one, I do need to do a u substitution. I can see that the inside function is the theta squared, so I'm going to let u equal theta squared, and then my du will be 2 theta d theta. So that's my substitution that I'm going to do. So to get this to work out, I will have sine of theta squared, and then I'll leave the theta here, d theta. So I just kind of scooch that over by the d theta. Then I need a 2 to show up, so I'll multiply a 2 in here and a 1/2 out here so that my du is showing up. When I do my substitution, now I'm ready to do the substitution. I'll have 1/2 integral of sine of u is theta squared, so sine of u, and then 2 theta d theta, that's my du. So an antiderivative of that would be negative cosine of u plus c. And now I need to go back to what u is and plug it in. So negative 1/2 cosine of 2 theta plus c. That's my final answer. For the next one, I can see that I do have a fundamental theorem of calculus part 2, but I have a function of x in the top bound, so it will need to be combined with chain rule. So I'll first start by plugging that in for both t's. So I'll have x squared to the 5th minus 9 times x squared cubed. And I want to multiply that by the derivative of the inside, which is just 2x. So you can leave it just like that. Okay, for the next one, I'm asked to find what all of these different things are. let's see. So the first expression is delta x, and if I look up at the picture, I can see that's represented by this c. And then f of x3 times delta x, so that will be this x3 is that height, delta x is this height, so that's going to be the area of this rectangle. So that will be A3. F of x3, that will be this y coordinate here, so that will be the height of B. And then the sum from 1 to n of all of those rectangles, that will be this sum here. So it'll be A1 plus A2 plus dot 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 plus AN. And then this one with the limit, that's going to be the actual integral from A to B of f of x dx. All right, for the next one, I'm given the graph of a function g, and I want to evaluate these numerical values. Okay, so g prime of 1, so that's going to be a positive value. So let's just start with figuring out what's positive and if anything's 0 or negative, and that'll be a good starting point. Okay, the integral from 1 to 5 of g of x dx, that will be this area underneath the curve. So that will definitely be positive. If I want to estimate about how big it is, I can see how many square units fit inside that. So I can kind of count the square units that fit inside of this. And I can see, you know, it's going to be in the neighborhood of 1, 2, 3, 4, 5, 6, 7, 8, 9-ish. So approximately 9 or 10, something like that. For this one, it is positive, but it's a slope. The slope is somewhere close to 1. So that's significantly smaller than the area underneath the curve, g of x from 1 to 5. Okay, the next one, I'm asked to find this. Let's see. So it's g of 1 plus 0.4k. So if I plug in k equals 1, it'll be g of 1.4 times 0.4 plus g of 1.8 times 0.4 plus blah, 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 plus the last one, when I plug in 10, it'll be g of 1 plus 4 times 0.4, so that's g of 5. So if I think about what that's representing, that is giving me a left-hand approximation, right? And so if this left-hand approximation is going to be above the curve, so that will be greater than this integral from 1 to 5 of g of x dx. Okay, and then this says g double prime of 1. So at 1, the function is concave down, so this is actually going to be negative. Okay, so the smallest of those is going to actually be the negative 1, so that's g double prime of 1, and the biggest of all of those is going to be the the right-hand sum. I don't know what I said earlier, but this is a right-hand sum because it's plugging in the right side of the interval. So this is that right-hand sum. So it's going to be the sum k equals 1 to 10 of g of 1 plus 0.4k times 0.4. Okay. So for the next one, I'm given that this Riemann sum is a right endpoint approximation for which of the following integrals. So I think it always helps to just write out a few of the terms. So I'll have 1 plus a half, so 1.5 cubed times a half, plus, for the next one, if I plug in 2, I'll have 2 sorry, it'll be 1 plus 2 over 2, so that'll be 1 plus 1, which is 2 cubed, times a half, plus dot, 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 and the last one will be, if I plug in 8, so 1 plus 1 half times 8, so that'll be 1 plus 4, so that'll be 5. 5 cubed times 1 half. Okay, so it looks like that this part is plugging in x values into the function. So my function, f of x, is going to be x cubed. It looks like this is a right-hand Riemann sum because I'm starting by adding, scooching over from 1 to some amount. So this is going to be a right-hand sum. And my interval is going to be from 1 to 5. On the right-hand side, I'm plugging in, the very last one, I'm plugging in the right-hand value, which is 5. And in the first one, I'm plugging in 1.5, which is going to be the right-hand side of that first interval. And so my delta x is a half, so I'm scooching over by 1/2 each time. So I should end up with this interval from 1 to 5. So I'm doing the integral from 1 to 5 of x cubed dx is what this is approximating. So that will be b. All right, so the next one says, this is a graph of my function. The expressions below represent numerical values. Which expression represents the largest numerical value? So the first one says f prime of pi over 2. So if I look at that, that is something positive. Okay. For the next one, it's f of pi minus f of pi over 2. So it's going to be this. It's going to be this slope here. So this one is actually still positive, but smaller than a. So both of those are positive, but, both of those are positive, but B is going to be smaller than A because it's not as steep, because A is a positive slope, but it's steeper. F double prime at pi. So at pi, my function is concave down, so this will be negative. The integral from pi to 2 pi of this, so from pi to 2 pi, if I'm looking at this area, what I'm going to see is by symmetry, these negative areas are the same as that positive area, so this will actually be equal to 0. And so this says which one is the largest, and the correct answer then would be A. A is the biggest positive value. For the next one, I'm just evaluating these integrals. So I'm going to find, for the first one, an antiderivative here. So I can plug in, I can just rewrite this as x to the minus 2 minus cosine x dx. So an antiderivative of x to the minus 2 will be, the power of x is going to go up 1, so negative 2 plus 1 is negative 1, and I'm going to divide by the new power. And then we know that sine has derivative cosine, so the antiderivative of cosine will be sine x, and then plus c. So I can rewrite this as negative x to the minus 1 minus sine x plus c. For the next one, I am asked to, this is going to be a u substitution. I'm going to let my u be natural log x. Then my du is 1 over x dx. So if I want to rewrite this, I'll have the integral from 1 to c of secant squared of natural log x times 1 over x dx. And so I can see that this here is my du. So if I'm ready to do my substitution, I'll have the integral of secant squared u du. And the x values are going from 1 to c. So I'm going to plug in, so whenever x equal 1, u is going to be natural log of 1, which is 0. And when x equals c, u is going to be natural log of c. So this goes from 0 to the natural log of c. And remember, natural log of c is just a number, okay? So we can just plug it in. So an antiderivative of secant squared is tangent of u from 0 to natural log of c. So if I plug that in, I'll get tangent of natural log of c minus tangent of 0. And if you plug that into your calculator, you'll see that tangent of 0 is just equal to 0. Okay, for the next one, I want to find the derivative of this integral. So again, this is Fundamental Theorem of Calculus Part 2, but notice that that's not just a plain x, it's actually an x, cubed. So I'm going to also involve the chain rule here. So to start, I'm going to plug that in for t. So sine of 4 to the x cubed, and then multiply that by the derivative of the inside function, which the inside function in this case is x cubed, so it'll be 3x squared. And that's my final answer for C. All right, for the next one, it says the graphs are graphs of the function g. Write an expression in each blank that represents the numerical value of the quantity described and identified on the corresponding graph. So the slope of the tangent line to the graph at 2, 2, that will be g prime of 2. The area bounded by the graph of g and the x-axis on the interval from 1 to 4, that will be this expression, integral from 1 to 4 of g of x dx. Okay, this is representing a right-hand Riemann sum with 3 intervals, so 3 rectangles, so that will be this one. Sum I equals 1 to 3, g of 1 plus I, and then the width of this is 1, so times 1, if you want to see that, times the delta x. The delta x in this case is just 1, so I'll write times 1 there just for emphasis. And then what is this? This is the average rate of change on the interval from x equals 0 to x equals 4. So that's this one. G of 4 minus g of 0 over 4 minus 0 will give us the slope of that line. Okay, the next one says the efficiency of a car on a road trip can be measured in how slowly fuel is burned. So if f of t is the rate at which fuel is burned, then the integral from 0 to 8 is going to represent the amount of fuel burned in the first 8 hours. So this is I could do a right endpoint approximation. Explain what the following represents. So this one will represent the amount of fuel burned in the, so that would be from, so I'm doing a right endpoint, so that's in the third, so I'm plugging in 3 delta t, that's this region. So that's the amount of fuel burned in the third it's this third time interval. I guess we don't know what our delta t is, so I don't know, the third time interval, whatever that is. This sum from 1 to n of f of ti, so this is the total, so this is an approximation of the total amount of fuel burned in the so my delta t, let's see, so we're looking at, this is approximation of that. Okay, so in the first 8 hours of the road trip, okay, And then this, if I let the number of rectangles go to infinity, that will give me the exact amount of fuel burned. In the 8-hour road trip. Well, or the first 8 hours, let's see. Oh, sorry, this is per minute. So all the places where I said hour, so it should be 8 minutes. And this should be in the first 8 minutes of the road trip. Okay.